Hello friends, welcome to CEC live lectures. Dear friends, as you know that we started a series on natural products and spectroscopy, and today we are conducting yet another lecture in the same series. In today's lecture, we will be discussing about the introduction of mass spectroscopy. In this part of the lecture, we will talk about introduction to mass spectroscopy as well as instrumentation, McLafferty rearrangement for different compounds. To discuss this topic, we have with us our subject expert, Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome, ma'am.
Thank you, ma'am. Hello viewers, in the series of natural products and spectroscopy, in the part of spectroscopy, I have discussed many topics like ultraviolet visible spectroscopy in details and their questions also. I have discussed IR spectroscopy, that is functional group spectroscopy. I have discussed also NMR spectroscopy in detail, and now the term is to discuss about the mass spectroscopy. I will discuss today the introductory part of mass spectroscopy, its instrumentation, and most importantly, McLafferty rearrangement. So, we have started with the definition of spectroscopy, and that involves the interaction of electromagnetic radiation with the matter. And you know, here matter is the organic compound. So, if you want to elucidate, if you want to set up the structure of organic compound, we need to take the help of advanced technology, that is spectroscopy, which involves the interaction of electromagnetic radiations. We have discussed in very first lecture about the various types of electromagnetic radiations and their characteristic properties, about their frequency, their energy. Study of spectroscopy deals with emission as well as absorption spectra. We have discussed this earlier also, and you know what is emission spectrum or spectroscopy? This is the spectrum which is produced by emission of radiant energy by an excited atom. It is excited by the fall of electromagnetic radiation. What is absorption spectrum? We generally study absorption spectrum. It is obtained by absorption of radiations of certain wavelength by a substance. So, now specifically today we will discuss about the mass spectroscopy or mass spectrometry. Mass spectrometry is the most accurate method for various things, like to measure relative molecular masses, or we can say molecular weights of organic compound with very high accuracy. Next point, to detect within a molecule the places at which it prefers to fragment. A molecule no more will have a identity, it will divide into various fragments. We will discuss in detail in coming slides. Unknown compounds can be identified by comparing their mass spectra with already available libraries software of the digital mass spectra of known compounds. So, you can identify the unknown compounds also with the help of mass spectroscopy. What we do in this technique? In this technique, organic molecules are basically bombarded with the electrons, and then these molecules to higher energetic positively charged ions, or we can say molecular ions, because these are generated from the molecule, or we can say parent ions. The molecules are ionized further and broken up into many smaller ions. These are also known as fragment ions or daughter ions. The loss of an electron from a molecule leads to a radical cation. The molecular ion, we can denote it like M plus with a radical dot, commonly decomposes to a pair of fragments which may be either a radical plus an ion or a small molecule plus a radical cation. You can see this is the molecular ion and these are the radical ions plus another fragment. This is neutral fragment, or it can be converted to these types. Each kind of ion has a particular ratio of mass to charge. We can say mass by E ratio. For most ions, the charge is 1. So we can say m by E ratio is simply molecular mass of the ion and nothing else. Here you can see an example. This is a structure formula of neopentane. When it is bombarded with the electron, it will convert it to a molecular ion. You can see it is C5H12. And when we calculate the molecular weight, it is 72. 12 multiplied by 5 plus 1 multiplied by 12, and when we added this, it is 72. So molecular ion has a value of M 72. Now if we see the fragmentation fragments or different fragments of molecular ion, these are the possible fragments. Number 1, how will it fragments? How a molecular ion will undergo a particular fragmentation, we will discuss in coming slides, because this is important thing. You can see there are different fragments ion, C4H9 plus, C3H5 plus, C2H5 plus, C2H3, and their different molecular weights. And you can see something, some other thing also here, relative intensity. What is this? I will discuss in detail in coming slides. It is, if we see this fragment, it is of 100 intensity, 100%, 41.5, 38.5, 15.7. The molecular ion is called the parent ion, we have told you, and is usually designated as M plus dot. It is positively charged molecule and with an unpaired electron. The set of ions, or we can say fragment ions or daughter ions, are analyzed in such a way that a signal is obtained for each value of that is represented by Me of each fragment. The intensity of each signal represents the relative abundance of the ion producing the signal. The largest peak in the structure is called the base peak. You must remember that, which is having the largest peak, or we can say the abundance is highest, and it is for reference is taken as 100. The intensities of other peaks are represented relative to the base peak, that is 100. You must be noted, molecular ion, or we can say parent ion peak, may not be confused with the base peak. It can be a parent ion peak or it can be a different peak also. The base peak has 100% abundance. Mass spectrum of a compound is plot which represents the intensities of the signals at various mass by E values. It is highly characteristic of a compound. No two compounds can have the exactly similar mass spectra as our fingerprints. A single mass spectrum is equivalent to dozens of physical properties of that compound for revealing the structure of that particular organic molecule. Mass spectra is used in two general ways. What is the application of this mass spectra? To prove the identity of two compounds, what actually organic molecules are, and to establish the structure of new compound. What does it mean to establish the structure of a new compound? For example, you have extracted compound from medicinal plant and you are not aware of the structure of that particular complex or a mixture of complex. So mass spectra help out you that what is the exact structure of that particular organic molecule or any component of organic molecule. The mass spectrum of a compound helps to establish the structure of a new compound in several different ways. How it helps you to elucidate the structure of a compound? It can give the exact molecular mass of the organic molecule. It can also give a molecular formula, or it can reveal the presence of certain structure units in a molecule. How it takes place, certain structure unit in the organic molecule, we will discuss in detail in coming slides. So we can say What is the theory of mass spectroscopy? A parent ion results when an electron is removed from the parent molecule. You can see this is the representation. This M is the molecular mass of the molecule, and when it is bombarded with the high energetic electrons, it gets converted to a ion, that is positively charged molecular ion. The MIE value of the parent ion is equal to the molecular mass of the compound. In a few cases, parent ion peak may be the base peak and it can be easily recognized. In most of the cases, parent ion peak is not the base peak and is often of very small abundance. Many elements occur naturally as isotopes. Out of these, the lightest one greatly predominates. The mass spectrometer is designed to perform three basic functions. Number one, to vaporize compounds of varying volatility. Number two, to produce ions from the neutral compounds in a vapor phase. Number three, to separate ions, different fragment ions made by the molecule according to their mass over charge ratio and to record them accordingly. The plot of M by E values taken along abscissa and their relative intensities along the ordinate in the mass spectrum. You can see this is the relative abundance and you can see this is the mass of the different fragments. This is the representation. It can give this kind of fragmentation or this kind of fragmentation depending on a particular molecule. We must notice that we should not forget this point while elucidating the mass spectrum of an organic compound. This is very, very important. Neutral particles produced in the process of fragmentation cannot be detected in the mass spectrum. So, one ion must be positively charged. You should remember that. This is the example of neopentane mass spectrum, and you can see different peaks related to different fragments ion. We have already seen the fragmentation pattern of neopentane, and you can see the relative abundance. Now, instrumentation part of mass spectroscopy. It consists of following parts. Number one, ion source. The first and an important step in obtaining the mass spectrum is to ionize the sample under examination. So, we have to ionize our molecule first of all. And the minimum energy required to ionize an atom or a molecule is called utilization potential. The common technique used for production of ion in mass spectrometer is by, we have taught about it, bombardment of the electrons, highly energetic electrons. The bombarding electrons are produced from an electrically heated tungsten filament. A few milligrams of the substance is produced as a vapor in the source at an operating pressure of 10⁻⁻⁶ mm pressure. So, this is the representation. These are the vapors. This is the tungsten filament, electrons producing from here, repeller potential, then acceleration potential and two analyzer. So, we have to produce a molecular ion, then the fragmentation fragments of different ions produced by the fragmentation pattern of a molecule, organic molecule. They have to be accelerated then in part B and then to analyze. The vapor is allowed to pass through slit A into the ion chamber. It is bombarded with a stream of electrons produced from a tungsten filament. The bombarding electrons have an energy of 70 electron volt. Due to bombardment, the molecule generally lose one electron to form a parent ion radical. And the bombardment of electron may result in the following types. These are the possibilities when an electron bombarded with an organic molecule. You can see this is the most probable possibility and this is the least probable. The energy required for removing one electron from the neutral parent molecule is usually 10 electron volt. With this much energy, no ions are formed. That is, no fragmentation of parent ion takes place. No doubt we will get the molecular ion, but further fragmentation will not take place. Then we need to supply more energy. So what about this energy? It is around 70 electron volt. Then additional energy is consumed in fragmenting the parent ion, that is the molecular ion. This results in the formation of different types of fragments ion, or we can say daughter ions of a molecular ion. The positive ion, whether even electrode or odd electron species, is deducted. So you must notice this point, that positively charged ion, or we can say a molecular ion or fragment ions, will be deducted by a mass spectrometer, whereas neutral molecules or radicals, you know what are radicals? Any species containing odd number of electrons will not detected by the mass spectrometer, and they will be leave as undetected fragment ions or parent ions. Mass analyzer. Second part of instrumentation from ion source is mass analyzer. The positively charged ion, parent ion or fragment ions produced in the ion chamber are accelerated by applying an acceleration potential. We need to accelerate them to analyze. So these ions then enter the mass analyzer. Here the fragment ions are differentiated on the basis of their mass to charge ratio, and the positive ions are directed through a slit B. I have shown you, this is the slit B. Only the positively charged ions will be accelerated by the acceleration potential, and this results in the formation of fragment ions or the daughter ions. These ions then enter the mass analyzer. Here the fragments are differentiated according to their mass charge ratio. The positive ions are directed through a slit B. I have shown you repeller potential is applied between point A and B, and the ions are accelerated by applying an acceleration potential of the order of 8 kilovolts through the slit C. Acceleration potential is applied between plates B and C. I have shown you the positive ions travel through whole of the analyzer portion of the mass spectrometer with very high velocity and are separated according to their mass to charge ratio. Here we are talking about first of all Dempster mass spectrometer, and this is used for this purpose. The positive ions travel in a circular path 180 degree under a magnetic field H. Suppose if an ion having a charge E is accelerated through a voltage V, then kinetic energy can be expressed, that is 1 by 2 mv square will be equals to EV. Small v is the velocity of ions after acceleration, whereas capital V is the potential applied for the fragmentation. It may be noted that a massive ion will travel slowly because it is heavy, slowly in a circular path, as compared to the lighter fragment due to the less mass or molecular weight. In a magnetic field H, any ion will experience force, and what will be that? In presence of magnetic field HEV, it produces an acceleration of V square by R in a circular path of radius R. You can see the radius half circular. These are the accelerated ion, and you can say after amplifier you will get a spectrum. This is Dempster mass spectrometer outline of. This is the Newton's second law of motion. When we are squaring both these sides, by solving it we get this kind of equation. What it shows? It shows that at a given magnetic field strength and accelerating voltage, the ions of mass by charge ratio value will follow a circular path. And what will be the radius of it? R. The ions of various mass to charge values reach the collector, amplifier, and then recorded by the spectrum. Instrumentation. The mass spectrum can be obtained either by changing the field, magnetic field H, or at a constant V, or we can do change in capital V, that is potential, accelerated potential at the constant magnetic field, that is H. We can choose either these conditions. When magnetic field is varied, that is H, the method is called magnetic scanning. It is called the electric voltage scanning when potential is varied at a constant field strength. So either you can change or either you can have the constant value. What is the modification, or we can say limitation, of Dempster mass spectrometer? The limitation in the above instrument is that the resolving power of the spectrum is limited by initial spread of translational energy of an ion leaving the source. The problem is overcome by passing the ions, you must be noticed that, through electric field prior to the magnetic field. So ions have to travel through the electric field as well as through the magnetic field, not only to the one field. They have to travel through both the field. First of all electric field and then magnetic. The electric field effects will cause focusing of the ions by placing a slit between the electrostatic and magnetic analyzers. The ions of closely defined kinetic energies can be thus selected prior to mass analysis. Instruments incorporating such a system are called double focusing mass spectrometer, which is actually are in use. These instruments are capable of attaining much higher resolving power. You know what is resolving power? How to interpret the spectrum of a particular organic molecule. If you can, if it is, there are fine intensities, or you can say there are fine relative abundance, then you can surely interpret it in an easy way. So it is possible to distinguish between the ions which have the same integral mass but different in exact masses. This may be possible for isotopes of elements which do not have integral masses. Here you can say the line representation of a double beam spectrophotometer. This shows the source slit. This is electrostatic analyzer, slit A, slit B, collector, then amplifier, then spectrum, and this is the second field, that is magnetic analyzer. Next part of the instrumentation is ion detector. No doubt we have studied till the fragmentation pattern. Now the ion detector part. The ions which are separated by the analyzer now have to detect measured electrically or photographically. The ion pass through the collecting slit one after the other and fall on the detector. The spectrum is scanned by going up the scale. The ion currents are amplified using a direct current amplifier, and the spectrum is recorded by using a fast scanning oscillograph. In this type of recording, 3 to 5 records of the same peaks are made with galvanometers having different sensitivities. So we have studied about the instrumentation part of mass spectroscopy. Now, what is mass spectrum? It is a record of masses and the relative abundances of the molecular ion. The positively charged fragments formed from it by the electron bombardment we have studied, and these ratios are taken along the abscissa while the relative abundances are taken along the ordinate. Base peak, we have studied it, is the highest peak, and it can be a molecular ion peak or it cannot be. And what is it? It is the most intense peak in the spectrum. Relative abundance of an ion means the percentage of the total ion current, which we are taking in ordinate in a mass spectrum. Now, we will talk about the molecular ion peak of parent ion. The electron bombardment with energy 10 to 15 electron volt usually removes an electron from the molecule of the organic compound in vapor phase. It results in the formation of molecular ion. The highest occupied orbital of aromatic system and non-bonding electron orbitals on oxygen and nitrogen atom readily lose one electron. An electron from double bond, 2 pi electrons or triple bond is usually lost. In alkanes, ionization of carbon-carbon sigma bond is easier than that of carbon-hydrogen bond because of the electronegativity difference. Here you can see the formation of different molecular ion, or we can say parent ion, from the different organic molecule. This is the master representation, and here you can see this is the benzene molecule, and what kind of parent ion? It will be a positively charged. This is the alcohol, aliphatic alcohol. You can see the parent ion, how you can represent. Here you can see, and this is the alkene, and this is the parent ion. So the mass of the parent ion gives the molecular mass of the sample. In the mass spectrum, it is important to locate the molecular ion at high mass region of the spectrum. The stability, this is the very important point, and I will discuss in detail in the coming slides. Stability of the parent or molecular ion decides its relative abundance. The peak intensity of the molecular ion differ from one compound to another. In some cases, parent ion peak is not formed, which means that the rate of decomposition of parent ion is too high for its detection. It is important to note that the rate of decomposition of the molecular ion increases with the increase in the molecular size. Larger molecule ion provide more possible reaction pathways for detection. So till now we have studied what is mass spectrum, how can we obtain a mass spectrum, what is the principles or theory of mass spectrum, what its uses. We have discussed about the in detail the instrumentation part of the mass spectrum, and we have also discussed about the mass spectrum, that is ordinate or relative abundance, and about the base peak, about the molecular ion peak. Hope you understood this.
Dear friends, in this part of the lecture on mass spectroscopy, we have come to understand its introduction and instrumentation. On that note, we are going to take a break, and after the break, we will be resuming with the lecture. Thank you for watching.
Thank you.
Hello friends, welcome to CEC live lectures. Dear friends, in this lecture on mass spectroscopy, so far we have discussed about its introduction and its instrumentation. In this part of the lecture, we will discuss about McLafferty rearrangement for different compounds as well as metastable ions. To discuss this topic, we have with us subjects by Dr. Vandana, and let's welcome Dr. Vandana and ask her to resume the lecture. Welcome, ma'am.
Thank you so much, ma'am. Hello viewers. In the In this lecture of mass spectroscopy, we have discussed about the basic principle of mass spectroscopy, fundamental of mass spectroscopy, about instrumentation part, and now I will start with the importance of molecular ion, that is found by the bombardment of highly energetic electron onto a molecule or an organic molecule. So let us discuss about the important features. We must remember that molecular ion peak in an organic compound is relatively much intense due to the presence of pi electron system. Conjugated olefins, that is the compounds containing alternate single and double bonds, show more intense molecular ion peak as compared to the corresponding non-conjugated olefins with the same number of unsaturation. No doubt unsaturation will be there, but conjugation will not be there. Conjugated olefins are more stable than the corresponding non-conjugated olefins. Unsaturated compound give more intense peak as compared to the saturated or the cyclic molecule. The relative abundance of the saturated hydrocarbon is more than the corresponding branch chain compound with the same number of carbon atoms. For example, the molecular ion peak for N-pentane is more intense than that of the new pentane because new pentane is much branched molecule as compared to the N-pentane. The substituent group like OH, alcoholic OR, alkoxy, amine, NH2, etc. increase the relative abundance in case of organic aromatic compounds. Also, the groups like nitro, NO2, cyano, CN, etc., which increase the ionization potential, decrease the relative abundance of the aromatic compound. The absence of molecular ion peak in the mass spectrum means that the compound under examination is a highly branched of tertiary alcohols. Primary and secondary alcohols give very small molecular ion peak. In case of chloro, so you can have an idea about the alcohol. In case of chloro or bromo compounds, look at the point. Isotope peaks are also formed along the molecular ion peak. So this is the specific point about mass spectroscopy, and you can see in case of bromo compound you will get two peaks, that is M plus molecular ion and M plus 2 peaks are formed in the intensity ratio, that is 1:1 ratio. Both the peaks will have the same intensity. So you can easily recognize the bromo molecules. And in case of chloro compound, both the peaks, that is M plus and M plus 2 peaks are formed in the intensity ratio of 1:3. Another important point about mass spectroscopy, you can notice nitrogen containing compounds with an odd number of nitrogen atoms in the molecule must have an odd molecular mass. An even number of nitrogen atoms or absence of nitrogen atoms in a compound show the molecular mass of the compound must be even. So you can immediately have an idea that if a nitrogen compound is in odd number, then molecular mass will be odd, and if a compound molecular formula is even nitrogen atom, then the molecular mass will be even in the same manner. Now the very important point in mass spectrum, determination of molecular formula. The mass spectrum is a plot, we are aware of it, representing the mass by electron values of the various ions. We can say fragment ions, daughter ions as well as parent ions against their corresponding relative abundances. The peak on the extreme right, that is the particle of highest mass, correspond to the molecular mass of the original molecule. In case of the straight chain hydrocarbons, the abundance of the parent ion peak is fair and it will give you M plus 1 peak also. Consider there is an example, a compound have these kind of fragment ion peak, different values 100, 85, 71, 57, 43. It is a straight chain because fragment peaks are formed 14 units apart. In case of a straight chain hydrocarbon, a peak due to C3H7 is the most abundant, or we can say it will be a base peak. So we can have an idea. Thus a molecular formula of the compound can be obtained in case an organic compound gives fragment as well as parent peak in pairs which are of 2 units apart. Then if the peaks are in 1:3 ratio, then it will be a chloro compound. I have taught you in the last slide. And if the peaks appear in the intensity ratio of 1:1, equal intensity, then it will be a bromo compound. So you can have quickly idea from the spectrum the peaks of intensity. If it is in 1:3 ratio, then chloro compound should be there, and if it is in 1:1 ratio, then bromo compound should be there. Let us determine the molecular formula of compound from the following mass spectrum. As pair of the peaks are equal intensity, I have told you in the last slide, it will be a bromo compound. And the isotopes are 79 bromine and 81 bromine. The pair on the extreme, you can see 79 value, the mass by electron values, and 81. The pair on the extreme right correspond to M plus and M plus 2 peaks. The spectrum correspond to the molecular formula C2H5Br. In some cases, we are talking about a very important topic, that is Mac-Lafferty rearrangement. That peak also gives an important clue in the determination of molecular formula. What is it? Actually, we will discuss in coming slide. For example, all straight chain aldehydes containing a gamma hydrogen atom form a base peak at a value of 44 mass per electron value. And this is called Mac-Lafferty rearrangement ion peak. Also in aldehydes, a fairly abundant molecular ion peak follows a less abundant M-1 peak. That suppose if it is have a molecular formula 59, then this less abundant peak will also appear, which is on 58 value. Let us consider a mass spectrum having mass by electron values at 72, 71, 44, which is 100%. So you can immediately have an idea it has a Mac-Lafferty rearrangement, because this 44 value is on 100% abundance. And you can see M plus and M plus minus 1 value peak also there. Another values are 43 and 29. So we have discussed this line 44, which is on 100% relativity, which is due to definitely Mac-Lafferty rearrangement ion in straight chain aldehyde containing a gamma hydrogen atom. And you can also say that it is a straight chain aldehyde. M plus peak at 72 also accompanies M minus 1 peak at 71. Clearly the compound will be CH3, CH2, CH2, CHO, a straight chain aldehyde. From the molecular formula 72, you can have idea for the molecular ion peak. You can calculate, because there are how many carbons are 1, 2, 3, 4 carbons. How many hydrogen? 3 plus 2 5 plus 2 7 plus 1 8 plus 1 oxygen. So immediately you can have a molecular formula because of these values. So what is actually Mac-Lafferty rearrangement? It involves the migration of gamma hydrogen. Here you can see with respect to this carbonyl group, this carbon is alpha, it is beta and it is gamma, and this gamma carbon have this hydrogen, so it is gamma carbon, gamma hydrogen, which involves the migration followed by cleavage of beta bond. This is alpha, this is beta, beta bond breakage is there. The rearrangement leads to the elimination of neutral molecule from aldehydes, ketones. Different types of compounds undergo Mac-Lafferty rearrangement, that is the migration of gamma hydrogen and cleavage of a beta bond. And the rearrangement proceeds through a sterically hindered 6-membered transition state. Here you can see this is the 6-membered 1, 2, 3, 4, 5, 6. 6-membered transition state. And you know what is transition state? Bond formation. Here you can see bond formation and bond breakage takes place simultaneously. So you can see it is a general compound ketone, and you will get this kind of molecular ion peak. Butanol. You can see this is the structure formula we write in a coiled form. Butanol contains a gamma hydrogen atom again, and the Mac-Lafferty rearrangement ion formed in this case. Here you can say this is the neutral molecule ethene and this is the charge fragment ion, and it will not detect. You are confirmed, it will not detect in mass spectrum, it will be detected by the mass spectrum. Similarly, a large number of organic compounds, for example ketones, amines, alcohols, esters, acids which contain a gamma hydrogen will undergo a Mac-Lafferty rearrangement and will produce a Mac-Lafferty ion, and that will immediately give an idea that what kind of fragment ion present in the organic molecule. Thus, the molecular formula of a known compound can be determined from the various fragment ions and also the parent ion of the molecule mass spectrum. Here are the other examples of Mac-Lafferty rearrangement. Here you can say this is 1-pentene, and how the Mac-Lafferty rearrangement took place, that is this gamma hydrogen will get shifted to or by the beta bond breakage. This is the neutral molecule and this is the fragment ion. Another molecule is there. Here you can see this is a ketone. You will get this kind of neutral molecule and this kind of fragment ion which will be detected in the mass spectrum. The structure requirement for this rearrangement is a side chain containing at least 3 carbon atoms. For a gamma hydrogen must be present, the last bearing a hydrogen atom and a double bond which may be a carbonyl group, as well as an olefinic double bond. You can see here there is no more carbonyl group. This is the gamma hydrogen, alpha beta gamma hydrogen, and this is the olefinic double bond. And propyl benzene shows a Mac-Lafferty rearrangement ion in a large abundance at a value of 92. So you can observe this kind of fragment ion and you can have an idea of this molecular ion. A double Mac-Lafferty rearrangement is also reported in certain ketones. Double Mac-Lafferty means 2 times Mac-Lafferty rearrangement takes place. The second hydrogen atom originates exclusively from the gamma position. A secondary hydrogen is preferred to primary hydrogen atom in this process. What will be the mechanism? Ketonization of the intermediate ion first of all takes place. You know how it takes place, by the hydrogen transfer. And where this hydrogen transfer? To the enol oxygen. Here you can see this is a ketone, simply 4-heptanone. How the Mac-Lafferty reagent takes place, you can see from here. This is the gamma hydrogen and here a bond, the molecule breaks from here, that is from the beta bond, and this is the molecule fragment ion. And you can see it is in enololic form because enol is here. Now the ketoenol tautomerism will take place by the transfer of this hydrogen to this carbon. So you can see the enolic form as well as the ketonic form. Then again a Mac-Lafferty rearrangement takes place because we knows what is the requirement of Mac-Lafferty rearrangement. We must have a gamma hydrogen attached to a carbonyl group, or we can say olefinic double bond. Here you can see this is the alpha beta gamma with respect to this carbonyl group. So another Mac-Lafferty rearrangement takes place and you will have another fragment ion. So you can observe this also. So we have discussed about the very important point Mac-Lafferty rearrangement, from which you can have an idea, quick idea of mass spectrum for a particular organic molecule. Now another important topic, what is metastable ions or metastable peaks? Metastable peaks are comparatively broad peaks. They are not sharp peaks. At where they are observed, you can notice it or you must remember this, these are observed at non-integer masses. They have low kinetic energy it must be noticed also. So, they will not reaches to the collector because they are not having appropriate kinetic energy to reach the collector. They have low kinetic energy. So, they are in between the instrument, they will not reaches to the collector. Then have the normal ions that arise from the fragmentation that takes place during flight down the ion tube rather than in ionization chamber. We have tacitly assumed that molecular ions formed in the ionization chamber do one of these two things. Either they decompose completely or very rapidly in the ion source and never reach to the collector, as in case of highly branched molecular ions, and which lifetimes, or we can say the life is less than 10 to the power minus 5 seconds. So, we cannot observe in the collector or in the amplifier. So, how the metastable ion takes place? You can see, consider this is the parent ion and this is the daughter ion. If this reaction, that is conversion of parent ion to daughter ion, takes place in the source, then the daughter ion, that is M1 plus, may travel the whole analyzer region and is recorded as, when it will recorded as M1 star ion, this is nothing but the representation of metastable ion. What is that? M1 starred ion. It is the representation of metastable ions. When it is not reaches to the collector, it is in between the instrumentation because of having the low kinetic energy, or we can say less translational energy. They are not accelerated much enough to the collector. On the other hand, if the transition M1 plus to M1 plus daughter, that is parent ion to daughter ion, occurs after the source exists before arrival at the collector, then this is called a metastable ion, no doubt. We know that in double focusing mass spectrophotometer, there are two field regions. One is the electrostatic region, another one is magnetic regions. These regions are called drift regions. Here you can see the graphical representation. This is the slit A, slit B. This is first region before the electrostatic analyzer, and before magnetic analyzer you can see this is the second field free region, and here you can see this is the collector. The ion pass through these regions after acceleration. The first field free regions refers to the portion of the ion path immediately before the electrostatic analyzer. The second field free region lies between the electrostatic analyzer, you can see in between electrostatic analyzer and magnetic analyzer. An ion with a charge E, after being accelerated through a potential V volts with possesses kinetic energy equal to EV, thus ion arriving at A point will have translation energy equal to EV, and thus energy of the ion will be independent of its mass. Now suppose the reaction, that parent ion to conversion to the daughter ion, occurs in the second field free region, not in the first free region. Then the daughter ion will have less kinetic energy, and this is M2 by M1 EV. And also the neutral particles, we can say M1 minus daughter M1 will have kinetic energy. You can see it will also have a less kinetic energy, because it is M1 minus small daughter ion mass divided by M1, that is molecular ion. It may be noted that the neutral particles, we have repeatedly saying, is not detected by the mass spectrometer. Thus M1 star, that is metastable ion formed in the second field free region, will have less kinetic energy than it would possess if it were formed in the source, that is the first free region. Clearly, the peak of the daughter ion will not be appear at the normal position on the mass scale. Instead, the signal will appear at this value. Hence, we can conclude that the position of the metastable peak due to this reaction, that is parent ion when converted to this daughter ion occurring in the second field region, or we can say it generates a metastable ion, and this will have this value. it is important to remember that for a reaction from a parent ion to a daughter ion, metastable peak has a distance below m on a mass scale, and the distance is approximately similar to distance that m lies below m1, that is daughter lies below parent ion. The relative abundance, because when it is not reached to the collector, the value will be small. The relative abundance of the metastable peak, that is m star, is often of the order of 10 to the power minus 2 or less as compared to the abundance of the parent ion or the daughter ion. Here is the example you can see. This is the molecular ion, and you can see by removal of this you will get this kind of metastable ion by the removal of this kind of radical. I want to make it notice that this radical will not detect in the mass spectrum. Now, how to calculate metastable peaks? What will be the exact values of metastable peaks? Because they are not reaching to the collector. So, we can calculate by this value, m star is equal to m1, that is value for the daughter ion whole square divided by the molecular mass of the parent ion. Consider the formation of metastable peaks in the spectrum of para-amino anisole. The parent molecular ion appears at 1, 2, 3 value. Suppose the fragmentation of parent ion into daughter ion due to the loss of methyl radical loss 15 mass, methyl radical CH3 takes place in between the electrostatic and the magnetic analyzer, that is in the second field free region. The position of the metastable peak can be calculated as, so here you can see the molecular ion peak will be observed at value of m by E 1, 2, 3, and the daughter ion will be available on 108, while the metastable peaks we can calculate in this way, and we will get the value of 94.8, which is not very far from the daughter ion. We see the position of metastable peak below m1, and it is approximately the same as m, that is same as daughter ion, and it is below than the parent ion, that is 1, 2, 3. We have studied, we have noticed that the parent ion will observe on 1, 2, 3 on the mass scale, which is linear. The position of the metastable peak due to the following fragmentation in the second field free region can also be determined. Here is the another example you can see. This is the daughter ion when it is converted to this kind of fragment by the removal of this carbon oxygen. It is a neutral molecule, so we can also calculate for this metastable peak, which will be approximately at 59.2 m by E. Another example is here. Consider the mass spectrum of toluene. This is the what is toluene? It is nothing but C6H5CH3. This is the molecular ion of the toluene. Two strong peaks at about 91 and 65 are observed. Now we have to see why they are observed. I mean to say by which fragment structure these are observed. Here you can see the peak at 91 is due to the formation of tropylium cation. This is what? This is a tropylium cation which is formed by the toluene ion, which loses a molecule of acetylene to give C5H5 at an abundance of 65 molecular mass will be there. So, I told you one thing, that which kind of fragmentation took place in a particular organic molecule. We can say that stability of fragments decide the availability, relative availability of the fragments. So, here you can see this is the tropylium ion which is very stable cation, so it will form at 91 and it can rearrange to benzyl cation. Suppose the transition C7H7 metastable ion to this occurs in the second field free region, then a metastable peak is formed and the position of broad metastable peak can be determined in this way. So, a metastable peak in case of toluene appears at the value of m by E, that is 46.4. Now, what is the importance of metastable peaks? The metastable peaks in the mass spectrum greatly contribute in the structure elucidation. From the position of parent ion and the daughter ion, the position of metastable state is calculated as above and can be confirmed in the spectrum under examination. So, in this lecture we have studied about the fundamentals of mass spectrum, about the importance of mass spectrum. We have studied how the mass spectrum can be studied, about the instrumentation part, about the fragmentation. I want to tell you, an organic molecule will give different fragmentation, but fragmentation, which kind of fragment ion will take place or which kind of daughter ion will take place from a parent ion or molecular ion is totally dependent upon the stability of that particular fragment ion. And we have also discussed about a very important point, that is Mac-Lafferty rearrangement. And how can you say that a particular molecule will undergo Mac-Lafferty rearrangement or not? Because you have to observe the gamma hydrogen which is attached to carbonyl group or olefinic carbon bond. So, if they are present, then you will definitely have a Mac-Lafferty ion over there, and you can elucidate the structure of a particular organic compound in an easy way. So, mass spectrum is a very effective mass spectroscopy to identify an unknown compound or to compare the different compounds. So, hope you understood this.
Dear friends, due to paucity of time, we have to stop our lecture here. On that note, we would like to thank Dr. Vandana for coming here and delivering this wonderful lecture. And thank you, dear friends, for watching our lecture. Stay tuned and keep watching. Thank you.
Thank you so much.